This tutorial is going to go through some new features in the powdR package. So I'm going to load the package. Not sure what powdR abind is. And then I'm going to run the web application using run_powdR. Then it should open in your default web browser. I use Firefox, which tends to be fine. So I'd recommend that. And the main things I want to show in this tutorial are some new features in this fourth tab called Full Pattern Summation. It used to be two separate tabs in previous versions, but from version 1.2, I've combined them into one tab for simplicity. So I just want to go through an example using data that can be downloaded here. I'm going to use the sandstone example, which is a soil developed on sandstone in combination with the library, an example library, which can be downloaded here. So it's just a very basic example. And I've already downloaded them, so I can load them in. Now for the mode, there are two options. There's a manual mode and an automated mode. I'm going to stick with manual for now, and also going to stick with these default options for the optimization routine and the objective function. These seem to be the most accurate in all the testing that I've done. So we get to step 5, which is selecting the phases to use in the fitting. Now, by default, it selects the first phase that it comes across in the library once it's loaded, but I don't actually want dolomite, so I'm going to delete that. And for starters, I want to add quartz. And when you begin to type in quartz, you'll see there are a few options to choose from. You can either choose quartz under the phase names heading, or a couple of quartz patterns under the phase IDs heading. By selecting quartz here, what I'm in essence doing is selecting both of these at the same time. So it just saves clicking really. So I'm going to select quartz, and then the next part of the process is to choose an internal standard that's going to be used here to align the peaks of the sample with the reference library. Now, the sample I've loaded, this sandstone, wasn't actually prepared with an internal standard, but we're going to use quartz as a kind of proxy internal standard. So here you can actually, if you have prepared it with an internal standard of a known concentration, you can tick the box and define it, but I haven't, so I'm going to leave that unticked. So I'm going to use quartz 1, you could use quartz 2 as well, to do the alignment. And later on, when we do automated full pattern summation, this internal standard is also used to help estimate limits of detection, and I'll explain that a bit later. For now, we'll leave all the other parameters as they are, and scroll back up to the top where we can click to do the computation. And when you're dealing with a larger number of reference patterns, this computation can take some time, but this is a simple example, so it finishes quite quickly, and you get a table of the phases used in the fit, along with their estimated concentrations calculated from the reference intensity ratios. And you also get an interactive graph displaying the measured pattern, fitted pattern, and the reference patterns that are contributing to the fit. So if we zoom in on the main peak here, we can see that the fitted pattern in red slightly overshoots the measured pattern in black, and the fitted pattern is made up of a contribution of quartz 1 and a larger contribution of quartz 2. So we have a fit, and you can zoom in and zoom out again by double clicking. So we have a fit, and quartz accounts for a lot of the big peaks we have in this sample, but there's a lot of the signal that we haven't accounted for, such as this. There's a big difference in the background here, and there's also a peak at about 7 angstroms that we haven't accounted for, and some peaks either side of the major quartz peaks. So by no means have we accounted for everything. Now there are various ways of identifying what phases account for these peaks, and one of the ways of doing it in powdR is to try using automated full pattern summation, which we'll have a go with in the next example. So we're going to keep the data all the same, and just change the mode to automated. And now what we want to do, we're not exactly sure what phases are in this sample. Well, I'll pretend I don't know. A mineralogist that's experienced at looking at soils might be able to take an educated guess, but here we're just going to throw all of the phases in the reference library at the fit. So I've selected everything that's available there. This is a small library, so there aren't many phases to choose from. And you'll see that now I've selected all of these. The internal standard has changed because it updates every time you modify the phases to use in the fitting. So I'm just going to go and make sure I choose the quartz pattern again. Now, I still don't know the internal standard concentration. And now you'll see that there are 2 further options that we can choose for automated full pattern summation. Here we can specify if any of them should be treated as amorphous. So here I'm going to treat organic matter as amorphous, and what that does is excludes it from the way in which limits of detection are calculated, which I'll explain in a bit more detail in a moment. And the second thing we can select is which phases should be forced to remain throughout, which can be useful in some cases, but we'll just leave that box blank here for the moment. So then we get down to the other parameters that we've just kept as the default so far. Got this alignment tab, which just allows you to modify how much the sample can shift be shifted along the 2 theta axis in order to align it to the internal standard, which is quartz. There's this shifting parameter, which is another kind of alignment routine whereby the reference patterns are all shifted by a small amount, by least squares optimization in order to improve the fit. And this is quite a computationally intensive process. So if you do allow this, you can increase the computation time quite a bit. So for this example, I'll just leave it at 0, but it's usually a very useful option to include because it gives you slightly more accurate results. And then down here at the bottom is another slider to represent what your estimate would be of the limit of detection of the internal standard. So quartz is our internal standard, and we can expect to be able to detect maybe 0.1% of quartz in a sample, and that'll change depending on what your internal standard is and your sample is. So let's go with those parameters for now. And what the automated approach will do is select the appropriate phases from this library using non-negative least squares, and then it will optimize the fit using this routine and this objective function. and then it will exclude any phase estimated to be below the limit of detection, which is based on a 0.1% limit of detection for quartz, and that will be used to calculate the limits of detection for all other phases based on their reference intensity ratios. So a reference pattern with a higher reference intensity ratio than quartz will have a lower limit of detection, and vice versa. So if we recompute, these computations can take a bit longer because you're throwing more phases at the optimization. So if you go back into our studio and have a look at what's going on, you'll see that you get notifications at various stages of the process. And once it's completed, you get a completion status. So if you go back to the fit, you'll see that we've got an updated table and an updated graph. And if we zoom in on the features of the graph, we'll see that now we have a far better fit. It's still not perfect because this is a very small reference library, and it's not quite able to account for some minor features. But in general, it's doing a far better job. And you'll notice how this blue line, the organic matter line, is what is accounting for the large difference in background that we had previously. And if we go up to look at the weight percentages of all these phases, you'll see that this sample actually has approximately 40% organic matter in it. And then there are minor features of potassium feldspar, kaolinite, and plagioclase. The kaolin is what is accounting for this 7 angstrom peak. So there are two ways of doing full pattern summation in this web application now. We've got automated and manual. Both have their niches, and if you want to export the results, if you're happy with the fit, you can go down to the bottom and download the fit as a RData file, and I'll save it there. And then you can load it again later or look at the results in the results viewer and editor tab, for which there's already another video tutorial. So if you're in that position, you can go and have a look at that video and try it out for yourself. So that just about sums up everything in this updated tab of the web application.